The soft murmur of leaves outside the window, a gentle susurrus against the deepening indigo of the evening sky, forms the immediate soundtrack to an inquiry that stretches far beyond the confines of this quiet room. Staring out into that vast, seemingly immutable blackness, peppered with the diamond dust of distant stars, one is inevitably drawn to the fundamental architecture of existence, spacetime itself. Is this cosmic stage, this four-dimensional continuum where all events unfold, merely a passive backdrop, a rigid stage upon which the drama of physics plays out, or is it something more akin to a living entity, constantly shifting, learning, and undergoing a relentless process of evolution? This is the central, mesmerizing core of the theory of the self-evolving cosmos, a concept that transforms the static universe of Newtonian mechanics into a dynamic, almost biological system, carrying us, its temporary inhabitants, along on its own grand, millennia-spanning journey of adaptation. To properly engage with this radical proposition, we must first lay a coherent foundation, much like settling into a comfortable armchair with a steaming cup of tea, ready to delve into complexity. Spacetime, as envisioned by the revolutionary mind of Albert Einstein, is not a dichotomy of separate spatial dimensions and temporal progression. Instead, as articulated through his theories of special and general relativity, they are inextricably interwoven into a single, unified manifold, spacetime. Imagine this fabric, supple yet incredibly robust, capable of being warped, stretched, and curved by the presence of mass and energy. The quintessential illustration remains the bowling ball dropped onto a tightly stretched rubber sheet. Its weight creates a profound depression, and smaller marbles rolling nearby inevitably curve inward, drawn not by some invisible tether, but by the geometry of the sheet itself. This geometric distortion is gravity. Einstein, with his penetrating gaze and the characteristic tousle of hair that hinted at the ceaseless activity within, spent years in the measured solitude of his Princeton office, the faint scratch of his pencil marking equations that fundamentally remapped reality, culminating in this elegant description in the early 20th century. But the profound leap required by the self-evolving universe hypothesis is to ask, does this spacetime continuum possess a form of life, meaning the capacity for autonomous change, the ability to learn from past configurations, and the drive toward developmental advancement? This inquiry fuels the debate surrounding the self-evolving universe, a concept sparking vibrant, often impassioned discussions among physicists, echoing late into the night at international conferences, punctuated by both skeptical murmurs and bursts of intellectual excitement. Now, we pivot to the intellectual epicenter of this hypothesis, largely formulated by the contemplative figure of Lee Smolin, a physicist whose very bearing suggests deep engagement with cosmic timescales, working at the Perimeter Institute in Canada. In the seminal year of 1992, Smolin introduced the concept of cosmological natural selection, a theory he meticulously elaborated in his 1997 volume, The Life of the Cosmos. The bedrock principle here is that our universe is not a singular, arbitrary accident, perfectly calibrated for complex chemistry, the anthropic principle's favored explanation, but rather one instantiation within a vast, perhaps infinite, metasystem undergoing Darwinian evolution. Envision the cosmos not as a collection of isolated islands, but as an immense, branching family tree. The mechanism proposed involves black holes. When a singularity forms within our universe, it might not lead to simple collapse, but rather to a bounce, birthing an entirely new baby universe in a region causally disconnected from our own. Crucially, this progeny universe inherits the fundamental physical constants such as the fine structure constant, the gravitational constant, or the speed of light from its parent, albeit with minute, random perturbations, akin to genetic mutations in biological inheritance. The universes that prove most successful at generating black holes, the most efficient reproducers in this cosmic lineage, will proliferate their constants across the multiverse landscape, leading to a selection pressure favoring high black hole production rates. Feel the intellectual shockwave of this realization. Smolin, perhaps surrounded by the low hum of cooling servers in his study, realizing that the very constants that permit the existence of sentient life on Earth might simply be a fortuitous byproduct, the necessary preconditions for complex organization coinciding with the conditions optimized for gravitational collapse and subsequent cosmic reproduction. This framework directly implicates spacetime in the concept of life. Within Smolin's model, spacetime is fundamentally dynamic, not an inert container. The laws governing physics, including the precise mathematical description of how spacetime curves and responds to energy density Einstein's field equations, which relate the metric tensor to the stress-energy tensor, are subject to variation across generations of universes. Imagine spacetime not as granite bedrock, but as a vibrant, flowing river system whose channels, depths, and currents gradually alter over eons due to erosion, tectonic shifts, and the accumulated history of its flow. In our observable universe, these laws appear fixed, constant, set in stone. However, under this hypothesis, spacetime, in conjunction with the laws that define it, is perpetually learning from the preceding universes, subtly adapting its parameters to favor the conditions that maximize reproductive success, in this case, the formation of singularities. This mechanism offers a profound alternative to the anthropic argument. The fine-tuning we observe is not luck or design, but the cumulative, statistically probable outcome of cosmic selection pressure over innumerable cycles. Yet, this theory attracts rigorous scrutiny. Critics like Leonard Susskind, whose presence in academic discourse often brings both intellectual rigor and a persuasive warmth, have pointed out a significant observational tension. The theory predicts that universes should evolve towards the maximal production of black holes, yet our universe, while certainly containing them, does not appear to be maximally geared toward their creation. This discrepancy fuels continuous refinement and heated debate in seminar rooms, where the air is thick with the smell of burnt coffee and relentless questioning. To fully appreciate the resonance of this idea, we must widen the aperture to encompass the deep history of human thought, recognizing that the yearning to see the cosmos as alive is not exclusively a modern scientific construct. Millennia ago, the foundational Greek philosophers, such as Aristotle, contemplated the essence of time and space under the shade of olive trees, the sea breeze whispering ancient narratives, often viewing time as an eternal, unbroken flux. In ancient India, the Vedic texts presented cosmology through cycles of immense duration, yugas, where universes were described as continuously being born, dissolving, and being reformed, mirroring Smolin's notion of a perpetually reproducing cosmic engine, the sounds of chanting echoing within temple sanctuaries. Across the Atlantic, the Maya civilization constructed their colossal observatories and stepped pyramids, their ceremonial drums marking profound temporal rhythms, perceiving time and space as potent, living forces directly influencing the fate and destiny of humanity. These ancestral narratives serve as a profound reminder. Regardless of technological era, the human mind instinctively recoils from the concept of absolute cosmic inertia, using myth and philosophy as early tools to probe the very dynamic realities modern science now attempts to model mathematically. Leaping forward to the current epoch, the early 21st century, scientific advancements continue to inject intoxicating complexity into this discussion. In a 2021 paper, The Autodidactic Universe, Smolin, in collaboration with thinkers such as Jaron Lanney, expanded the framework, suggesting the universe functions less like a simple Darwinian mechanism and more like a vast, self-teaching neural network. In this analogy, the laws of physics, the very substrate of spacetime, are seen as evolving data points, with the universe adapting its rules based on the outcomes of previous cosmological states, analogous to how artificial intelligence refines its weights based on training data. Imagine the sheer intellectual exhilaration within the Perimeter Institute as researchers analyze these intricate mathematical formulations, the pale glow of monitors illuminating faces alight with discovery, recognizing the implication that spacetime might possess a form of cosmological memory, archiving successful physical strategies from preceding universes. By 2025, the initial findings from the James Webb Space Telescope, peering back to just a few 100 million years post-Big Bang, revealing surprisingly mature, early supermassive black holes, offer indirect, tantalizing support for a rapidly evolving cosmological landscape, one where the conditions for gravitational collapse were established earlier than standard models might have predicted. Furthermore, cutting-edge work emerging from theoretical physics centers in 2025 introduces the notion of cosmological natural selection with intelligence, or CNSI, a provocative extension where the emergence of self-aware, technologically advanced civilizations like our own might actively participate in seeding or shaping the next generation of universes, prompting jubilation among researchers like Andy Gardner in dimly lit conference rooms, fueled by strong black coffee. And the energy of paradigm shifts. The direct observational evidence supporting the mechanism of cosmic reproduction, the black hole birthing process, continues to mount through gravitational wave astronomy. The detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, first announced in 2016 and continuously upgraded since, acts as an audible echo from the deepest trenches of spacetime. These ripples, stretching and squeezing the very metric of space as they pass, represent the violent collision and merger of massive compact objects, primarily black holes. Consider the electric anticipation felt by pioneers like Kip Thorne as that initial, faint signal registered, a palpable thrumming that suggested we were finally eavesdropping on the mechanics of cosmic creation. Recent high-precision analyses of these mergers, extending into 2025, strengthen the correlation between extreme gravitational events and the potential boundaries of spacetime itself. Concurrently, explorations into the concept of phase space, the total space of all possible states a system can occupy, are being redefined. Some theorists now suggest that spacetime, as we perceive it with its smooth geometry, is merely the macroscopic, low-energy manifestation, the surface of a far richer, fundamentally discrete, and self-organizing quantum structure. Caleb Schoff, in his highly anticipated 2025 publication, Is Space the Place for Earth's Next Evolutionary Leap?, speculates boldly that the development of life and complex consciousness on Earth might not just be a biological accident, but a crucial, emergent property of the universe actively seeking greater complexity, perhaps even acting as the precursor to the next reproductive cycle, rendering our existence simultaneously infinitesimally small and cosmically significant. The investigation inevitably pushes us toward the quantum realm, where the rigid structure of spacetime dissolves into probabilities, becoming the crucial, yet most elusive, bridge between gravity and the strange laws governing the very small. Near the event horizon of a black hole, where spacetime curvature becomes infinitely steep according to classical general relativity, the quantum nature of reality asserts itself violently, leading to predicted phenomena like Hawking radiation. This is the boundary where time seems to stop for an outside observer, and space itself appears to fray. To suggest spacetime lives here implies that its evolution is governed by quantum probabilities, that the very structure of reality is being negotiated moment to moment through quantum mechanics, perhaps echoing interpretations like cubism, where the physical world is deeply tied to the observer's state of knowledge or belief. This quantum dance resonates disturbingly with research in neuroscience, specifically the work by researchers like Andrew Newberg regarding the brain's response during deep meditative or spiritual states. These states, characterized by specific patterns of decreased activity in the parietal lobe, are correlated with profound feelings of unity and transcendence, a sense of touching a reality beyond the mundane three spatial dimensions and linear time. If consciousness is, in fact, the universe's mechanism for observing and perhaps even selecting successful physical laws, then the subjective experience of living may be the most critical component of the self-evolving cosmic process, making the mind an essential element of spacetime's ongoing self-discovery. Viewing this process through the lens of galactic architecture provides tangible anchor points. Consider the supermassive black hole residing at the heart of our own Milky Way, Sagittarius A star, an entity boasting a mass equivalent to 4 million suns. The images captured by the Event Horizon Telescope, most recently refined in 2025 data releases, reveal its characteristic shadow encircled by a brilliant corona of superheated plasma, a halo of incandescent energy framing an absolute void. Imagine the sensory experience of approaching such an object, the incomprehensible tidal forces beginning to distort reality, the air temperature plummeting to near absolute zero at the edge of the photon sphere, yet the mind is gripped by an awe that transcends physical sensation. Recent cosmological models, informed by the continuous simulation of black hole genesis within the context of Smolin's framework, posit that the very Big Bang that initiated our spacetime could have been the singular, explosive birth event originating from the collapse of a black hole in a preceding meta-universe. This circularity, where the end state of one cosmological epoch dictates the initial conditions of the next, is the heart of the self-evolutionary narrative, a narrative championed by those who see complexity arising necessarily from iterative selection. The human element remains integral to this sweeping cosmic story. Consider Lee Smolin himself, who, despite facing persistent theoretical roadblocks and skeptical reviews, retains an infectious optimism, often pausing mid-explanation to smile while articulating the possibility of an evolving cosmos, an attitude that fuels generations of young researchers. Or think of Janna Levin, whose talent lies in translating these impenetrable mathematical landscapes into narratives that possess the clarity and emotional depth of poetry, treating the evolution of physical law as an unfolding drama. They remind us that science, at its most ambitious, is deeply personal, driven by an intrinsic, sometimes almost painful, curiosity that causes the heart rate to quicken in the face of the unknown. Ultimately, this journey into the animated nature of spacetime compels a re-evaluation of our place within it. If spacetime is indeed living, evolving through iterative refinement, driven by the physical imperative to maximize reproductive complexity via black hole formation, then the universe is not a finished product, but an ongoing act of self-transformation, where order necessarily arises from preceding chaos. To look up at the night sky now, feeling the cool breath of the evening wind on one's face, is to invite the imagination to participate in this grand process. We are situated within an entity that is actively exploring its own mathematical possibility space. The universe, in its relentless quest to generate more instances of itself, is waiting to be understood, and perhaps, the development of complex, self-aware consciousness, our ability to ask these very questions, is not merely an effect, but the emergent mechanism by which the living fabric of spacetime observes and directs its own infinite future.